Hi everyone. I want to apologize in advance if you guys can hear my dog bark. He's been barking a lot, so I've been having to record this so many times. But this is going to be your pre-lab lecture for gas chromatography. This is an online lab for all three groups, Group A, B, and C. As always, make sure you guys read your lab manual ahead of time. That way you guys have everything you need for your quiz. Make sure you watch these 4 videos. Complete your pre-lab notebook in a timely manner because I don't want you guys to get behind. Complete your pre-lab quiz. It is due before every Wednesday at 8 in the morning, regardless if you're in group A, B, or C. Your post-lab notebook is due before 11:59 p.m. every Sunday, and this is the data that everybody's going to be using depending on your first name. Okay, let's get started. Okay, gas chromatography. It is a widely used technique to separate complex mixtures of substances. Compounds that are present in a volatile liquid or gaseous solute are oscillated after traveling through a coated column based on the substance's size and intermolecular interactions. The level of binding experience between the substances and the column is a nonpolar column because gas chromatography is reversed phase chromatography, is determined based on the number and strength of intermolecular interactions between the two species. Substances that pass quickly through the column exhibit fewer intermolecular interactions with the column. Sorry. The Vernier-Mini gas chromatography. It utilizes a metal column with a nonpolar coating, which is the stationary phase. The stationary phase retains solutes of the same polarity. A sample consisting of one or more samples is injected into the column and is carried through the stationary phase by atmospheric air. So, your nonpolar coating is going to be your stationary phase, and your atmospheric air is going to be your mobile phase. Organic compounds flowing out of the chromatography column are then detected by a chemical sensor that produces electrical responses proportional to the concentration of the compounds. The presence of such a chemical detector is seen as a peak on your graph. Retention time, the unique time it takes for a compound to exit the column after it is injected. Retention time can identify a compound from a mixture. So let's say you have 2 compounds. Compound A has a low boiling point. Compound B has a high boiling point. If it has a low boiling point, that means it's going to leave faster and your retention time is going to be shorter. That means compound A is going to have a shorter retention time and compound B is going to have a high retention time. Now, it's not always boiling points that affect retention times. There's other things that affect it as well. So, factors that affect retention time. Sorry, I can't read the top one, so I'm going to exit it. More volatile compounds, like I said, a lower boiling point, will move through the column faster because they flow in the mobile phase and don't strongly bond with a stationary phase. Surface functional groups also affected. So, for example, alcohols may weakly bond with the polar stationary phase more than esters, and that is because alcohols can form hydrogen bonds. Also, the molecular weight, the heavier the molecule, the slower it will travel through your GC column. Instrument settings. When separating compounds with a wide range of boiling points and polarities, it helps to raise the column temperature during separation. Temperature programming reduces elution times of highly retained compounds. Pressure adjustment. Higher pressure causes greater strain on the intermolecular interactions between the compound and the stationary phase, which in fact reduces the retention time. GC analysis and calculations. Now I'm going to read this and then I'm going to show you something I wrote to see if it helps a little bit more. To determine the area for each peak, measure its height and width. The area of the peak is equal to 1/2 width times height. To determine the ratio of each compound in the mixture, you will add all the areas together to get a total. The percent composition of any compound in the mixture is equal to its area divided by the total area of all the peaks in the sample. Now, that is a lot of words, and I know you guys are probably like, what? So, let me get out of here. Okay, so pretend you have your spectra. You have a peak right here, you have another peak right here. peak A and peak B. It doesn't matter which one's shorter, which one's taller. Just imagine a graph with a spectrum graph. So your peak A has an area and your peak B has an area. To find that area, you're going to multiply height times width and then half that. And for peak B, you're going to do the same thing, half height times width. Now, you're going to get a value for that area, correct? So when you add these two values, you're going to get a total area. The total area is all the peaks added together, okay? Now, if you only have one peak, you're going to calculate the area the same way. You're going to get your value, but there's no other peak. So your total area will be the area of that one peak you have, okay? Now, your percent composition. So we're going back to if you have two peaks in your graphs. So first, percent composition for peak A is going to be your area for peak A, which was this value we gathered up here, divided by the total area of that graph that you made with the two peaks, okay? Don't use, if you have different graphs, do not use the total area for the other graphs. Only use the total area corresponding to the peaks you have on that one graph, okay? So your percent composition for peak B will be the area for peak B, this value, divided by the total area. So the area of peak A plus the area of peak B. Now, if we want to calculate the percent composition for this one peak, let's say this is one graph we got, and this is a second graph. So our percent composition is going to be very different from this one peak because they have different areas. So to calculate this percent composition, we would use the area for peak A divided by the total area of this peak. I just want you guys to keep in mind, do not confuse your total areas. Your total areas belong to each graph. They're very different they're very distinct from each other depending on the graph. And I'm going to show you what I mean by graphs. Okay, so let me get out of here. Actually, let me finish this and then I'll go back to Canvas to show you guys the graphs. So the objectives: measure and analyze a mixture of three compounds as they pass through the GC. Measure and analyze each compound in a mixture individually using the GC. Measure and analyze each fraction collected during previous fractional distillation experiments. Now, we used to do fractional distillation first and then gas chromatography and collect 3 fractions from fractional distillation to then analyze them in the gas chromatography lab. But given COVID and that we're doing a lab in person and a lab online, that is not going to happen. Instead, you will be doing this step right here during fractional distillation when you come into lab, okay? So if you want to add a change, we're not going to be doing this part. Okay. What to include in the lab report. For your pre-lab, post-lab calculations, area of the peak and percent composition, this is going to be coming from your GC spectra. Your changes, do not force the syringe. This is going to account for your fractional distillation lab next week. So make sure that when you are putting it into the GC, you do not force the syringe. They're very expensive and they're very delicate. Graphs that need to be included: acetone to butanone to pentanone and a ketone mix. So that is it. Let me go back to Canvas. I'm just going to click a random one. All right, so as you can see right here, there's only one peak. That means the total area that you're going to be calculating only belongs to this peak. Do not use the total area you gathered here for this graph, okay? I think that I explained it a little bit better now. So over here, you only have one peak too. It's going to have its own individual percent composition, its own individual total area, its own individual peak area. Same thing right here, only one peak. And you can tell you only have one peak because it's only one compound. Ketone mix. This is a mix. So as you can see, you have 3 peaks. When you are doing your discussion, make sure you add why did you get that percent composition? What do you know about the retention time? Why are they so close to the zero, or why are they so far from the zero in time? Make sure you include all of that and you discuss why. Okay. And that is all I have. So if you guys have any questions, message in the group me. If it's more of a question that you only want to ask me, please email me. Do not send a message through GroupMe. If it's a message that can be answered through GroupMe, that everybody can contribute, send it through there. If not, send me an email. Also, please give me a 24-hour window to answer questions, because sometimes I get questions on Sunday, like around 4, 7, and I probably won't have time to answer them really fast. So please give me about a day before your complete lab notebook is due. And that is it for this video. So yeah, bye.